Welcome to this explainer. Today, we are taking a dynamic programming journey, and we're going to demystify the whole concept by transforming a naive, brute force approach into a highly optimized, seriously elegant solution. Have you ever looked at a coding problem and literally felt your brain tie itself into knots trying to figure out where to even begin? Well, you are definitely not alone. We are going to tackle a total classic today, the minimum coin combination. And by the end of this, you won't just know how to solve this specific problem, you're going to understand the actual core philosophy of dynamic programming itself. Okay, let's just jump right into this brain teaser. Imagine you're standing at a cash register, right? And you have an infinite supply of $1, $2, and $3 coins just sitting in your pocket. Your target is to pay exactly $5. But here is the catch. What's the absolute fastest way to make that $5? Using the fewest number of coins possible. Now, you probably solved that in like 2 seconds flat in your head. You just grab one $3 coin, one $2 coin. Boom. That's 2 coins, and you're done. But translating that human intuition into efficient computer logic, that's surprisingly tricky. Because, a computer doesn't have intuition. It only has instructions. So we have to take this optimization journey together to figure out exactly how to teach a machine to find this minimum combination, without it taking until the end of time to do it. All right, first up, breaking it down with the top-down approach. Let's start with how a computer might most naturally try to solve this. Basically, we start with our big goal, our target amount, and we try to just chip away at it, piece by piece. So the absolute crucial thing to grasp here is that every time we decide to use a coin, we inherently create a brand new subproblem. Think about it. If our target is 5 and we test out using a $3 coin, we just subtract 3 from 5. Now our new target is 2. The whole problem has shifted. We now need to find the minimum number of coins to make $2. We basically took a big problem and broke a piece off to make a slightly smaller problem. But here's the thing. The computer doesn't actually know which coin is the best choice right off the bat, so it has to try all of them. As we try every possible coin in our array, the 1, the 2, and the 3, we start to branch out. Using the $1 coin drops our target to 4. Using the 2 drops it to 3. Using the 3 drops it to 2. We're continually reducing our target, and in the process, creating 3 distinct new subproblems that we now have to go and solve. And wow, this right here brilliantly illustrates the fatal flaw of this naive top-down method. Because we have an unlimited supply of coins, the computer is going to aggressively try every single path. Even for a tiny target like 5, the branches literally explode into a massive chaotic tree. Every subproblem creates 3 more subproblems, and those create 3 more. If our target hits 0, awesome, we found a valid combination. Those are the green check marks. If it goes negative, marked by the red X, it's an invalid path. But the sheer volume of calculations here is just staggering. If our target was 100 instead of 5, the computer would likely just freeze up entirely. So let's move on to our next section, memoization, and how it saves us a ton of time. Clearly, blindly trying every single path is a total disaster for performance. To fix this massive inefficiency, we need a clever trick to trim this overgrown tree and bring everything back down to reality. That trick is a foundational concept called memoization. And look, despite the super fancy name, memoization is basically just forcing the algorithm to write down its answers on a notepad so it doesn't have to do the exact same homework twice. If it solves a subproblem once, it saves the answer. Next time it sees that exact same problem, it just checks its notepad instead of recalculating the whole thing from scratch. Let's look back at our messy brute force tree for a second. Notice those highlighted sections? We are calculating the exact same subproblem for target equals 3 completely from scratch on the left side of the tree, and then doing it all over again in the middle of the tree. The computer's just wasting precious time doing identical work. In computer science, we call these overlapping subproblems. But watch how elegantly memoization fixes this issue. See how those green arrows link back to an already solved path? The very first time the computer figures out the minimum coins for a target of 3, it saves that answer. Then later, when the right side of the tree asks for a target of 3 again, the algorithm is like, wait, I know this, and instantly points back to the saved answer. It completely chops off that entire redundant branch of the tree, which means we calculate each target exactly once. And the math completely backs up the magic here. Without memoization, our time complexity is this terrifying O of n to the power of target divided by m. That's exponential time, meaning the computation time just skyrockets to infinity with larger numbers. But once we add memoization, We chalk way down to O of target multiplied by n. We go from an agonizingly slow, program-crashing nightmare down to a highly efficient linear-like sweep. Next up, let's talk about flipping it, the bottom-up approach.
Okay, so we've successfully optimized the top-down method using memorization. That's great, but we are not quite done. Senior engineers and coding interviewers, they love to flip this entire paradigm upside down for the ultimate, cleanest possible solution. Instead of starting all the way up at our target of 5 and awkwardly subtracting our way down to 0, what if we started at 0 and built upwards? In the bottom-up approach, we initialize a dynamic programming array, usually just called a DP array. We start right at the base case, where our target is 0. And how many coins does it take to make $0? Exactly 0 coins. From that rock-solid foundation, we build our way up to 5.
Let's actually walk through these exact steps and see how this builds algorithmically. Step 1, we start a loop at target 1. Step 2, we check all our available coins to see which ones fit. Step 3, we update our DP array with the minimum coins needed for that specific target. And we do this by relying on the answers for the smaller targets we literally just solved moments ago. And finally, step 4, we keep repeating this until we hit our final target of 5. We solve for 1, then 2, then 3, then 4, and finally 5. We build on our previous answers every single step of the way. The real beauty of this bottom-up approach, it maintains that excellent optimized time complexity of O of target times n, absolutely. But it structures the logic so cleanly using only a one-dimensional space array, which keeps our space complexity to an incredibly light O of target. There's no messy recursion, no deep call stacks eating up all your memory. It's just a straightforward, highly efficient loop. All right, before we wrap up, a quick pro tip on spotting dynamic programming. Understanding the minimum coin problem is fantastic, but recognizing when to actually use these concepts in the wild, that's a true superpower. Read this quote from our source material carefully. These specific adjectives, minimum, maximum, longest, shortest, they are huge, waving red flags in problem descriptions. Whenever you see them, it almost certainly means you're dealing with a problem that wants you to optimize a certain value. And optimization is the exact environment where dynamic programming just absolutely thrives. So you've totally conquered the minimum coin problem. You know exactly how to turn a chaotic tree of infinite possibilities into a sleek, streamlined array. Keep this logic right in your back pocket. The next time you're staring down a coding challenge, look for those key words. Ask yourself, what other intimidating algorithm puzzles can you absolutely crush using the power of dynamic programming? Keep exploring, keep optimizing, and I'll see you in the next explainer.